Hello everyone. Today we'll continue our discussion on expectations of different types of random variables. Let us revise the definition. Expectation of simple random variable is simply weighted mean of its possible values, where weights are the probabilities of those values. Then expectation of a non-negative random variable is obtained as a limit of sequence of expectations of simple random variable, and expectation of an arbitrary random variable is obtained via expectations of positive and negative parts of that random variable. Okay, so now using these definitions, we have already proved that expectation of simple random variable has certain properties such as linearity, etc. Today we will try to discuss similar properties for arbitrary or non-negative random variables. So let me first list down all the properties that we are going to try and prove. So x1 and x2 are any two random variables. So x1 and x2 are random variables defined on omega script a p. Further, we will say that expectation of x1, expectation of x2 and expectation of x1 plus x2 exist. Okay, then we will try to prove similar properties like those proved for simple random variable. So if if x1 is non-negative almost surely, then expected x1 is also greater than or equal to 0. So this is known as non-negativity. Then expectation of cx1 is same as c expected x1, where c is any real number. Then if x1 is 0 almost surely, then expected x1 is 0. Next part is linearity. So expectation of x1 plus x2 is actually expected x1 plus expected x2. Then if x1 is greater than or equal to x2 almost surely, then expected x1 is greater than or equal to expected x2. So this is monotonicity. If x1 is integrable, then mod x1 is also integrable, and vice versa. So x1 is integrable if and only if mod x1 is integrable. And we'll have one more property. Let me write it down. If mod x1 is less than or equal to y and y is integrable, then x1 is also integrable. Okay, so if mod x1 is less than or equal to y and y is integrable, then x1 is also integrable. Okay, so before starting with these properties, there are a couple of smaller results which might come in handy while proving these things. So let me start with those results first. So one of the result is about expectation of an indicator function. Okay, so How do you define expectation of an indicator function? So indicator function takes only two values. Indicator of any set A takes value 0 if omega is not in A, so omega is in A complement, and it takes value 1 if omega is in A. So basically indicator is a simple function. As a result, expectation of indicator would be 1 into probability of A plus 0 into probability of A complement. So this becomes probability of A. So what does it mean? Expectation of indicator is integral of indicator function with respect to dp over omega. So this we are saying is same as probability of A. Okay. Then if I want expectation of x into indicator function, how can I write this? So this becomes integral over omega x I A dp. Okay. So this I can write as integral over A xia dp plus integral over A complement xia dp, because A union A complement is omega. Is it okay? And A and A complement are of course disjoint. Now on this region indicator of A is 1. So this becomes integral x dp over A plus on this region indicator A complement is indicator A is 0 because we are in A complement. As a result the integrand is 0 everywhere and hence integral is 0. Okay. So the important result is xia dp. When you integrate over entire omega, it is actually same as integral of x over just A. Okay. This result also we may need somewhere. Then there is one more result. I would state it, I won't prove it. So if probability of A is equal to 0, then integral x indicator A dp over omega, which is same as integral over A of x dp, is 0. Okay. So if probability of A is 0, then over that set, if I consider expectation type of integral, then it is 0. Okay, we won't go into proof of it, but we might need this result somewhere. Now let us try to prove the results that we want to prove. The first one is monotonicity. So if x1 is, but monotonicity only with respect to 0 we are saying. So if x1 is non-negative, can we say expectation x1 is non-negative? Okay. Remember, we already know this result for simple random variables. So we are going to make use of it. Now x1 is greater than or equal to 0 almost surely. Okay. So we can say that let n be a set. So let n be a set of all those omegas such that x1 omega is greater than or equal to 0. Okay. And what we know is probability of n is 1 because x1 is greater than or equal to 0 almost surely. So this means, so expectation of x1 can be written as integral x1 dp over entire omega. Okay. And this can be written as integral x1 dp over n plus integral x1 dp over n complement, because n union n complement is going to be entire omega. Now we just said that if probability of A is 0, then integral of x over that A is always 0. Here we are already saying that probability of n complement is 0. So this part of the expectation will never contribute. This will always be 0. So we have to worry only about this. Okay, so we have to worry about integral x1 indicator n dp over omega from the result that we stated just now. So this is expectation x1 indicator n. Okay, so expectation of x1 is actually same as expectation of x1 into indicator of n. Okay, now can we say that this x1 indicator n is a non-negative random variable? X1 is non-negative almost surely. So x1 is not completely non-negative. There might be some values of x1 which are negative, just that probability of those values is 0. However, for x1 indicator n, this is always greater than or equal to 0 because on n, x1 is non-negative. So whenever indicator n is 1, x1 is non-negative, so this holds. And whenever x1 is negative, at that time indicator n is 0. As a result, the product is 0, so this still holds. Okay. So now that this is a non-negative random variable, there exists a sequence, a non-decreasing sequence of non-negative simple random variables. Let me call them x1n's such that x1n converges to x1 indicator n. Okay, this small n has nothing to do with the capital N. Okay, small n is representing the indexing thing in the sequence. Okay. And we know that since each x1n is non-negative, expectation of x1n is also greater than or equal to 0. This is by property of simple random variables, property of expectation of simple random variable. Okay. Expectation of x1 indicator n is written as limit over n going to infinity expectation of x1n. That is our definition. And because each of these numbers is non-negative, limit of a sequence of non-negative numbers cannot be negative. So this has to be greater than or equal to 0. Okay. And we have already seen that expectation of x1 indicator n is nothing but expectation of x1. Hence, we have proved that if x1 is greater than or equal to 0, then it's even almost surely, even if it is just almost surely greater than or equal to 0, still its expectation is greater than or equal to 0. Okay. Now, next result is about multiplication by a constant. So, we have to prove that expectation of Cx1 is C times expected x1 for every C in R, and we don't have any condition on x1 also. So x1 can be non-negative, negative, arbitrary, anything. Okay. Of course, for simple random variables, we have already proved this, but now we have to prove for non-negative and arbitrary. So let us first assume that x1 is greater than or equal to 0 and C is also greater than 0. Okay. Then, since x1 is greater than or equal to 0, there exists a non-decreasing sequence of non-negative simple random variables x1n. There exists a non-decreasing sequence of non-negative simple random variables x1n such that x1n converges to x1. Okay. And now we are saying C is greater than 0. So Cx1n converges to Cx1, and Cx1n is a non-decreasing sequence of again non-negative simple random variables because C is positive. Okay. Therefore, expectation of Cx1 can be defined as limit over n going to infinity Cx1n. Now you might feel that Cx1 is a non-negative random variable, so there may exist some another sequence of non-negative simple random variables which converges to Cx1. Why take only this sequence? But there is a result which says that if you construct any sequence which converges to a non-negative random variable, and if that sequence has these properties, means it is non-decreasing and it is a sequence of non-negative simple random variables, then if you compute limit of expectation via that sequence, the limit is always the same. So whichever sequence you get, finally the limit is same. Okay. And we know Cx1 is a simple random variable, and we know for simple random variable C can be taken outside the expectation. So this is limit n going to infinity C expected x1n. C can be taken outside the limit also, so it becomes C limit n going to infinity expected x1n. So this is equal to C times expected x1. This is exactly what we want, but of course we have proved it only for non-negative x1 and positive C. Okay. To see what happens when C is negative, let me first prove another simple result. What happens to expectation of minus x when x is arbitrary? Not necessarily x is non-negative, when x is arbitrary. So when x is arbitrary, how do we define expectation? Expectation x is defined as expectation of positive part of x minus expectation of negative part of x. Okay. How do we define positive part? X plus is x if x is greater than 0 and 0 if x is less than or equal to 0. So we can define x plus as x into indicator of x greater than 0. Okay. Because on the other set indicator is 0, so anyway the product will be 0. Everyone getting this? Similarly, x minus is defined as minus x if x is negative and 0 if x is positive. So x minus can be written as minus x into indicator of x greater than 0. Okay. So we will make use of this and we'll prove a simple property that expectation of minus x is same as minus expectation of x. This we will prove. Okay. I know you have used this result like hundreds of times, but we have never formally proved it through this integration or major theory approach. So let us try to prove it. So for that I need what is positive part of minus x and what is negative part. So positive part of minus x by definition would be minus x into indicator of minus x greater than 0. What I am doing is, in this definition I am just putting minus x instead of x. Okay. So minus x, positive part of minus x would be minus x into indicator of minus x greater than 0. But this is same as minus x. Now minus x is greater than 0 means x is less than 0. So it becomes integral of x less than 0. And what is this? Minus x into integral x less than 0 is nothing but negative part of original x. Okay. Similarly, you can prove that negative part of x would be by definition minus x into indicator minus x less than 0. Minus of minus x is plus x, so it is plus x indicator minus x is less than 0 means x is greater than 0. Okay. And what is this? X into indicator x greater than 0 is nothing but x plus. Okay. So positive part of x is same as negative part of minus x, and negative part of x is same as positive part of minus x. Okay. Using this, now let me write expectation of x minus. So expectation of x minus by definition would have to be expectation of minus x would be, by definition, expectation of positive part of minus x minus expectation of negative part of minus x. We just saw that positive part of minus x is nothing but negative part of original x, and negative part of minus x is positive part of original x. So this is, if I take minus sign common, expected x plus minus expected x minus. So this is expected x, of course, with a negative sign, which we have already taken common. Okay. Hence we have proved that expectation of minus x is minus expectation of x. Okay. So this is an important result. We are going to use it while proving this expectation of cx is equal to c into expected x. Okay. Now expectation of cx, let us consider the case where c is negative and x is positive or non-negative. So c is negative, x is non-negative. So this can be written as, let k is equal to minus c, and minus c will be positive. So this can be written as expectation of minus kx. Okay so far? Because k is minus c, so c is minus k. And we just proved the result that expectation of minus x is minus expected x. So this becomes minus expectation of kx. Okay. And because k is positive and we know that expectation of kx would be k expected x, let me write this as minus k expected x, and minus k is c, so this is c expected x. Okay. So what we have proved is, now for a non-negative random variable x, if you multiply by any c, it's either negative or positive, and of course 0, then expected cx is c expected x. Okay. Now we have to prove for arbitrary random variables. So now let x be arbitrary and c also be arbitrary. So expectation of cx by definition would be expectation of positive part of cx minus expectation of negative part of cx. Okay. Now we know that positive part and negative part both are non-negative random variables. Okay. One small thing we still need to address: what happens to positive part of cx and negative part of cx depending on c. So cx plus would be, let me assume for the time being c is positive. So cx plus would be cx if x is positive, because c is anyway positive, and it would be 0 if x is negative. Okay. So cx plus is cx into indicator of x greater than 0, I can say. Okay. Similarly, cx minus would be minus cx if x is negative and 0 otherwise. So cx minus would be minus cx into indicator of x less than 0. Okay. So what is this? So I can say, at least in this context, means when c is positive, that cx plus is actually c times x plus, and cx minus is actually c times x minus. Okay, this is true when c is positive. In general, it may not be true. So using this result, let us try to simplify things further. So we are trying to find expectation of cx. So that becomes expectation of c times x plus minus expectation of c times x minus, at least when c is positive. So this is c times expected x plus, because now x plus is non-negative, c is non-negative, so cx plus is non-negative, and for non-negative thing we know this, minus c times expectation of x minus, so this becomes c times expected x. So now we have proved the result when c is positive and x can be arbitrary. So now the only case that remains is c is negative and x is arbitrary. Okay, so let c be negative and x be arbitrary. Now c is negative, so again we'll introduce k as minus c, so k is positive. Expectation of cx can be written as expectation of minus kx. Again it would become minus k expected x. Okay. Let me check if we have proved it for general x or if we have proved it only for negative. Yeah, we have proved for general, right? So minus k expected x, and minus k is nothing but one step. Okay, let me write down one more step. We shouldn't skip steps. Okay, so expectation of minus kx I can write as minus expected kx. So this result we have proved that negative sign can be taken outside from expectation of arbitrary random variable, and minus, now k is positive, so just now we proved that this can be written as minus k into x, so this becomes c expected x. Now we'll prove the next result. If x1 is non-negative, x1 is 0 almost surely, then expectation of x1 is 0. If x1 is 0 almost surely, I can write x1 is non-negative almost surely. Therefore, I will get expectation of x1 is greater than or equal to 0. Similarly, I can write x1 is negative almost surely, right? Which is equivalent to saying minus x1 is greater than or equal to 0 almost surely. So, expectation of minus x1 is greater than or equal to 0, and expectation of minus x1 is minus x1, so it is greater than or equal to 0. Therefore, expected x1 is less than or equal to 0. Hence, combining the two, we get expected x1 is 0 almost surely. Okay, so combining this with this. So we have proved that if x1 is 0 almost surely, then expected x1 is also 0 almost surely. Let me skip the fourth result. Let me first try 5th, 6th and 7th, and then we will come back to the fourth one. Okay. So the fifth property says that if x1 is greater than or equal to x2 almost surely, then expected x1 is greater than or equal to expected x2. So we will use the same thing. We will define x1 minus x2. So x1 minus x2 is greater than or equal to 0. So expected x1 minus x2 should be greater than or equal to 0. And assuming that we have proved fourth result, this would become expected x1 minus expected x2, assuming we have proved fourth. Okay. Therefore, we get expected x1 is greater than or equal to expected x2. Is it okay? Expectations are constant, so we won't say this is greater than or equal to this almost surely or anything like that. These are constants. These are random variables, hence almost surely can come into picture. Okay. Next result is x1 is integrable if and only if mod x is integrable. Mod x1 is integrable. Now, we will go back to the definitions of x1 and mod x1 in terms of their positive and negative parts. So, we know x1 can be written as x1 plus minus x1 minus, and mod x1 can be written as x1 plus mod x1 can be written as x1 plus x1. Okay, and expectations are also defined from these things. Okay, so if x1 is integrable, then that means x1 plus and x1 minus are also integrable, because x1 is integrable means expected x1 is finite. Expected x1 is finite if and only if expected x1 plus and expected x1 minus both are finite, and if those two are finite, then their addition is also finite. So expectation of mod x1 is also finite. Is it okay? Same thing we can do for reverse way. Means if expectation of mod x1 is finite, then both these expectations are finite, and hence expectation of x1 is finite. Okay. The last result is if mod x is less than or equal to y, if mod x1 is less than or equal to y and expectation of y is finite, then x1 is also integrable. That is the result. Okay. Now mod x1 is less than or equal to y, therefore we can write expectation of mod x1 is less than or equal to expectation of y by monotonicity, and this is finite. So we have expectation of mod x1 less than infinity, and therefore expectation of x1 is also less than infinity, because we just saw that x1 is integrable if and only if mod x1 is integrable. Okay. So except for fourth we have proved everything. So now let us try to prove fourth. I won't give you the entire proof. We will discuss the idea and then you can fill in the details. So the fourth property is linearity. Expectation of x1 plus x2 is equal to expected x1 plus expected x2. This we have to prove. First, let us consider the easiest case. x1 and x2 are non-negative. So if x1 and x2 are non-negative, in fact even almost surely, then x1 plus x2 will be non-negative, almost surely. Okay, it can be negative. Now, there exists a non-decreasing sequence xn, x1n of simple random variables such that expectation of x1n converges to expected x1. Similarly, there exists another another non-decreasing sequence of simple random variables such that each of them is non-negative, and expectation of x2n converges to expectation of x2. Okay. Actually, the original result would say x1n converges to x1, x2n converges to x2, and hence the expectations can be defined. So the sequence x1n plus x2n is also non-decreasing, right? If two sequences are non-decreasing, their addition is also non-decreasing, and it is also a sequence of non-negative simple random variables. So expectation of x1 plus x2 can be defined as limit over n going to infinity of expectation of x1n plus x2n. So this can be defined as limit over n going to infinity expected x1n plus limit over n going to infinity expected x2n. So this is expected x1 plus expected x2. So if both x1 and x2 are non-negative, then the result is automatically true. We have just proved it. Now the question arises when they are arbitrary. Okay, either one or both. So what the idea of the proof is, we divide the entire omega into different parts. So what are those parts? Part where both x1 x2 are non-negative and hence x1 plus x2 is also non-negative. Then another part where x1 is less than 0, x2 is less than 0 and hence x1 plus x2 is also less than 0. You can have another part where x1 is non-negative, x2 is negative, x1 plus x2 can be anything. So one possibility we have to consider x1 plus x2 positive. Another possibility in the same setup we have to consider x1 plus x2 negative. Then the reverse possibility. So x1 is negative, x2 is greater than or equal to 0 and x1 plus x2 greater than or equal to 0 and x1 negative, x2 positive but x1 plus x2 negative. So have we covered all possibilities? So these are 6 possibilities. So on this part we know the result is true, we have proved. So let me call these sets as A1, A2. So set of all omegas on which this happens, we will call that as A1. Then set of all omegas on which this happens, we will call that as A2. Similarly, I'll have A3, A4, A5, A6. Okay. Integral of x1 plus x2 over entire omega can be split into each of these integrals. So integral of x1 plus x2 over a1, integral of x1 plus x2 over a2, etc. So if we can prove this result of addition individually for each AIs, then also we are done. Okay. So even for each AI we can prove that expectation of x1 plus x2 is expected x1 plus expected x2, then we are done. So for the first part we already know. For the second part, let us try. So everything is negative. On A2, everything is negative. So let us consider that case. So x1 is negative, x2 is negative and x1 plus x2 is also negative. Okay. Now, x1 is negative means minus x1 is positive, minus x2 is positive and minus of x1 plus x2 is positive. So using the result for positive thing, I can say that expectation of minus of x1 plus x2 is expectation of minus x1 minus x2. Okay, so this is expectation of minus x1 plus minus x2. Okay, so far. And we know minus x1 is positive, minus x2 is positive. So it can be written as expected minus x1 plus expected minus x2. And we have proved this result that this is nothing but minus expected x1 plus minus expected x2, which is minus of expected x1 plus expected x2. And this we know LHS is minus of expected x1 plus x2. So cancelling minus sign from both sides, we get that even when everything is negative, the result is true. Okay. Now your homework is to try for other 4 cases. So how to handle when one is positive, one is negative. Okay. The proof is not difficult. So just try to write down whatever results we have obtained so far and try to see how they can be used for this. Okay. So let me stop here. Thank you.